Hi guys, today we're going to start our last chapter. All right, I'm going to try to break this up into two different parts. We'll see if Zoom lets me lecture this whole part in one piece. And that chapter is about gases, okay? How gases behave, how we can predict their behavior, that sort of thing. Okay, so let's start by talking about what exactly a gas is like. We've discussed this before, but we're going to go into a lot more detail about it now. Things to remember here is that gas matter has a lot of space between the atoms or the particles that make it up, all right? A lot of empty space. So this allows them to move very freely past one another, okay? That empty space also makes gases what we call compressible, which means we can squeeze them into smaller spaces if we want to, right? Because there is a lot of empty space that makes them up. Gases are always going to take the shape of the container that they're in, and they are always going to adjust to occupy the volume of the container that they're in. And they can do that because there's so much empty space between them. Gases move very fast, and they move in straight lines, okay? The particles or the atoms or the molecules, they move in straight lines in the container that they're in until they collide with something else. All right, now this collision could be between other gas particles. The collision could be between the walls of the container. But the collisions are what they're what changes the direction that the gas particles are moving in, because these particles will move from point A to point B in a straight line until they hit something else. Okay, so this is kind of what that looks like. Now what you do see here is these points where your gas particles are actually colliding with the surface of the container that they're in. These collisions are what causes pressure in a container. Okay, so when we're talking about the gas pressure of a container, we're talking about what happens as a result of the collisions between the gas particles and the surface of the container that they're occupying. And we calculate pressure by looking at the force that's being applied over a particular area. Okay, that is our definition of pressure. So what we have are gas particles that are constantly moving and that are constantly interacting with the surface of the container that they're in. Okay, that is going to result in a particular pressure of the gas in the container. And this pressure is going to depend on how much gas is present, right? Because if we have more gas particles, we're going to have more collisions. That would affect the pressure. It's going to depend on the volume of the container, because a bigger container would have less pressure in it because there would be fewer collisions. A smaller container would have more pressure. And it's going to depend on the speed of the particles, because particles that are moving faster are going to interact with the surface more often than particles that are slower. Okay. Well, I kind of just went over this, but I guess I've laid it out here also. So when we're talking about the number of gas particles, as the concentration decreases, the concentration of gas particles decreases, the pressure will decrease, and vice versa. For the volume of the container, as the volume decreases, the concentration of the gas technically increases, because concentration is number of particles over the volume of the container, right? So if the volume gets smaller, the volume's the denominator there. If the volume gets smaller, the concentration is going to get larger. But you can also think about that in practical terms, like if you have 5 gas particles in a container and you make the container smaller, they have less room, so they're going to hit the sides of the container more. If you make it bigger, well, then they have more room, so they're going to hit the sides of the container less. Now, this is a visualization of the difference that concentration or number of gas particles makes on the pressure of a gas in a particular container. We have two containers here that are the same volume, they're the same size. Over here we have much fewer particles of the gas. Here we have a ton, right? So all of these gas particles here, they're hitting the sides of the container almost constantly, and that's going to result in a very high pressure. We have many fewer collisions in this example, so we have a much lower pressure here. When we talk about pressure, we're going to be talking about it in terms of particular units. These units you have to be very comfortable in converting in and out of, all right? So keep this conversion table handy and be able to convert. These are the only pressure units that you have to memorize. There are more, but your textbook limits our discussion to these 5. So and also note here, it's technically 6, but because these are kind of the same, we don't have to worry about another number to memorize. 1 torr and 1 millimeter mercury is the same unit, and they get used kind of interchangeably. So just note that for yourself. Atmosphere is the most common one, and that's our most important unit because it will be in the ideal gas law, which we'll be talking about shortly. And the other ones are just, they're common units of pressure that you see. Inches of mercury you see, pounds per square inch. That's like the pressure units that you see in tires, all right? And Pascal is another pressure unit that's common. Okay, so let's look at a few conversion problems to start with. A high performance road bicycle tire is inflated to a total pressure of 132 psi. What is this pressure in millimeters of mercury? Okay, so for this question, we're going to have to convert using the values that are on this table. Okay, so we want to go from psi to millimeters of mercury. Now, the good part about the way that this table is set up is that it's set up so that all of these values that are given here, you know, the 101, 325, 14.7, those all equal 1 atmosphere. Okay, and the table is set up this way because in the ideal gas law, atmosphere is required. So they're giving us a way to relate any of these pressure units back to atmosphere. All right, so that's helpful. But what we also are able to do is we can relate any of these units to one another. So 14.7 psi is equal to 1 atmosphere. 760 millimeters of mercury is equal to 1 atmosphere. That means that 14.7 psi is equal to 760 millimeters of mercury, or 760 torr. Again, those units are the same. So let's look at how we solve this. Okay, so we set up our problem. Okay, we want to know how many millimeters of mercury are equal to 132 psi. So now we're going to set up our first conversion. We have psi up top, so we're going to put it on the bottom here. And we're going to put millimeters of mercury on the top. And now we're going to use our conversion table to fill in the numbers. So we see that 14.7 psi is equal to 760 millimeters of mercury, and that's an exact number, so that's not going to play into our significant figures. Okay, and now we have to do some calculator work. 132 times 760 divided by 14.7, and we get 6.82 times 10 to the 3 millimeters of mercury. Okay, so these are like any other conversion problems that we would handle. So let's move on to the next example that's in your packet. I'm going to erase this and then look at the numbers there. Okay, so here's the second example, the one that's on your next slide. In this one, we want to know how many psi are there in 30.44 inches of mercury. Okay, so in this case, we're going to have to go from inches of mercury into PSI. So we look at our table and we see that there's 29.92 inches of mercury in 14.7 PSI. See where units cancel out there. All right, let's put that into our calculators. 30.44 times 14.7 divided by 29.92. Okay, we get 14.96, which we're going to have to round to 15.0 PSI so that we can keep our three significant figures there. Okay. And we have one more example. I believe converted pressure of converted pressure of 23.8 inches mercury to kilopascals. Okay, so how many kilopascals equals 23.8 inches mercury? Okay, so now the first thing that we want to do is we want to get out of inches of mercury and we want to go into Pascal because that is the measurement. That's the number that we have in that table. So 29.92 inches of mercury is 101,325 Pascal. Okay, but we want our final answer in kilopascal. That's a metric thing, right? So we figure that there are 1,000 pascals in 1 kilopascal. Right, and now we'll grab our calculators. 23.8 times 101,325 divided by 29.92 divided by 1,000, and we get 80.6 kilopascals. All right, so those are some of the basic conversions that we have to do with our pressure units. Nothing too crazy, it's not hard, but you have to be able to go back and forth very easily so that we can put all of our problems in the units that we need them to work with our gases. So let's talk a minute about how we measure pressure, okay? We can measure pressure with something called a barometer, okay? A barometer helps us measure the atmospheric pressure, right? So whenever you're listening to a weather report or something and they're telling you what the barometric pressure is, which is, you know, our outside pressure, our atmospheric pressure, they measure that with a barometer. We can measure samples of gases using something similar but with a slight modification, and that's called a manometer, okay? Now this is like a U-shaped tube, right? And it's going to be filled partially, not completely, with something like, I mean, mercury is not a great thing to use anymore, I get it, but it's very helpful in terms of measurement. You know, mercury thermometers were used for a long time because of that. And the same thing with manometers. So it's filled with some kind of liquid. We'll say it's mercury-like, okay? And the tube is connected on one side. Let me just take a picture, put the picture up here so that we can actually visualize this. So over here, we have the sample gas that we're looking at, okay? So you have a sample of gas, you don't know what its pressure is. So you put it in a container and you attach it to this U-shaped tube, okay? On one side, it's gonna be open to the atmosphere. And we know what the atmospheric pressure is because we've measured it with a barometer. Now, the atmosphere pressure and the gas sample pressure are both going to push on the liquid that's inside this U-shaped tube, okay? So that's what this point here is talking about. A competition is established between the pressures of the atmosphere and the gas. So they're both going to be pushing down on that liquid. But one of them is going to have a greater pressure than the other. And the one that has the greater pressure is going to be able to push the liquid down further. Okay, so in this case, the sample gas and the atmosphere were both pushing down on this mercury. But the gas sample had a higher pressure than the atmosphere, so it was able to push it down further, and then the liquid moved up closer to the atmospheric pressure opening. Okay, so that's how we can tell whether something has a higher pressure or a lower pressure than our atmospheric pressure. And we can actually measure that value. Okay, so we can take a measurement from the level of the liquid on the atmospheric pressure side to the level of the liquid on the sample pressure side, and we can measure that height difference. And that height difference we can actually add or subtract directly to the atmospheric pressure, which is a value that we know, and that will give us the pressure of our sample gas. Okay? So let's look at an example here. Now we are given a barometric pressure of 751.55 millimeters of mercury. Okay, so we have a barometer, we took the atmospheric pressure, and we know what it is. So we know this value here, this atmospheric pressure value, we know that it's 751.55 millimeters of mercury. Now we want to calculate the pressure of the gas sample, right? So we have our gas sample in here. Now our gas sample and our atmospheric pressure were both pushing down on the liquid, and the atmospheric pressure was able to push down further. So that means that our atmospheric pressure is greater than our sample pressure in this case. Now to calculate what the actual pressure of our sample is, we have to take our measurement of our H value. So we're going to look at the liquid level here and the liquid level here, and we're going to measure the distance between those two levels. And there's usually a zero line that's directly in between them that helps us take that measurement, because it's easier to measure from 0 down and then from 0 up, and then to add those two numbers together. Okay, so if I measure from my 0 to the top of the liquid line here, it's around 1.1 centimeters. If I measure from my 0 down to the liquid level here, it's about 1.1 centimeters. That means that the total height that I'm looking for is 1.1 plus 1.1 centimeters. Okay, or 2.2 centimeters. Now, two things I need to focus on at this point. Okay, so I wrote them out here so that we could really see this. Because our atmospheric pressure is greater than our sample pressure, our H value is going to be negative. Now, we make the H value negative so that when we add the two numbers together, so that when we add the barometric pressure and the H value together, we get a number that's smaller than our barometric pressure. Okay, because our atmospheric pressure should be a bigger number than our sample pressure. We also have to take this centimeter value and we have to turn it into a millimeter value, because our barometric pressure is in millimeters of mercury, not centimeters of mercury. Okay, so our H value went from 2.2 centimeters to negative 2.2 centimeters to negative 22 millimeters of mercury. And this is in the case where we have an atmospheric pressure that is greater than our sample pressure. Now all that's left to do is to add them together. And we get a pressure of our sample that's around 730 millimeters of mercury. And our final sample gas pressure is going to be smaller than our barometric pressure, as it should be. Okay. So here's another example. I'm going to switch over to the whiteboard so that we can solve this on there. We still have a total pressure of 751 millimeters of mercury. Okay. So in this case, this is our sample gas. And that's the atmosphere. So that'll be 751.55. Okay, in this case, our sample gas was able to push down much further than our atmospheric pressure. Okay, so that means that our sample gas has a higher pressure. Okay, that's the first thing that we can note from this. Now we have to figure out what this H value is. Okay, now in this case, we know that our H value will be positive because our sample has a higher pressure than our barometric pressure. And I kind of made these calculations, like maybe you can see them on your paper. This is an example that you can find in your textbook as well if you want to look at a bigger, nicer picture of it. But you would hopefully be able to see the measurements that I took here. So if we go from 0 up, we see that it's about 3.1 centimeters till we get to that liquid line. And then if we look at the bottom of the liquid line and we go from 0 to the bottom of it, it's also 3.1 centimeters. So our total here is around 6.2 centimeters. Right? So now we want to take our positive 6.2 centimeters we want to turn it into millimeters, and that is our H value. Now that we have our H value, we can take our 62 millimeters of mercury. We'll add it to our atmospheric pressure. Let's do our calculator. 62 plus 751.5. And that gives us 813.55. So we'll say 8.1 times 10 to the 2 millimeters of mercury. Okay. Okay, so now that brings us into the beginnings of our discussion about the ideal gas law, which is really where we're gonna stay very focused on for the duration of this lecture. You have to know this formula by heart, okay? You're gonna use it so many times and you're gonna use it kind of like forever in your chemistry career. This guy always comes back, all right? So we are going to use our 4 basic properties of a gas, and that is pressure, volume, temperature, and the amount of gas. And we're going to turn it into a relationship. Okay, so these things are all related to one another. And that relationship is that pressure times volume equals moles of a gas times a gas constant times temperature. Okay. Each of these properties are going to be reported in a particular unit in order to relate it to our gas constant. Okay, so whatever units our gas constant here has, those are the units that each of our properties here has to follow as well. And I will go into that more in a few slides, okay? So if you don't get entirely what I said right now, don't worry about it. We'll talk about it again in a few minutes. We pulled the ideal gas law out of what are called the simple gas laws, okay? The simple gas laws paired up 2 of these properties at a time and looked at the relationship between them, okay? And then out of the simple gas laws, the ideal gas law kind of emerged from there. Okay, so we saw the end product. The end product is PV equals nRT. These are the simple gas laws that came from. Okay, so each of these properties, pressure, volume, temperature, and moles, they're interrelated. That means that when one of them changes, it's going to affect the other properties. And each of these laws that we're talking about now, the simple gas laws, they're going to describe specific relationships between pairs of properties. Okay, so we're going to only look at two properties at a time, and we're going to hold the other two properties constant. So we'll start with Boyle's law. Boyle's law focuses specifically on volume and pressure and the fact that they have an inverse relationship. That means that when one increases, the other property will decrease. So as pressure increases, volume will decrease as long as temperature and the amount of gas is held constant. Okay, it's very important to specify that we're holding temperature and the amount of gas constant for this relationship to be true. Okay, but if we are holding the temperature and the amount of gas constant, then as pressure increases, volume will decrease. As pressure decreases, volume will increase. And they're going to increase and decrease by the same factor. Okay? This is a visualization of what's happening in there. So we can picture why this happens, right? Say that we have a setup like this, where we have a constant temperature and we have a constant moles of gas, right? We're not going to change anything here. And we are going to take, instead of having 1 kilogram on top, 1 kilogram will be like an indication of our pressure. Now there's a 2 kilogram weight on top. Okay, and what happens? It's going to move this platform down, and now the volume in here has decreased, right? We had a pretty large volume in here before. Now we've almost halved that volume, right? So we went from 1 liter to 0.5 liters. Well, now look at all the collisions that are happening. Like, I know you can't actually see them, but maybe you can imagine how many more collisions would happen in a much smaller space. That increased number of collisions is going to increase our pressure. So let's look at some examples of Boyle's law. Okay, I'm going to switch over to the whiteboard for this. Okay. A woman has an initial lung volume of 2.75 liters, which is filled with air at an atmospheric pressure of 1.02 atmospheres. If she increases her lung volume to 3.25 liters without inhaling any additional air, what is the pressure in her lungs? So we can imagine in the scenario that the temperature is not going to change because, you know, you're still in the same place. You're not doing anything special to temperature. And that last line where it says without inhaling any additional air, that's their way of explaining that we're not increasing the number of moles of gas either. So the only thing that we're looking at here is that we have an initial pressure of 2.75 liters. Was an initial volume, sorry. An initial pressure of 1.02 atmospheres. And that she's going to increase her lung volume to 3.25 liters. Okay. So if we're increasing her lung volume, we would expect to be decreasing this pressure amount. So let's see what happens. We have P1 times V1 equals P2 times V2. 1.02 atmospheres times 2.75 liters equals P2 times 3.25 liters. .02 times 2.75 divided by 3.25, and we get 0.86. 3 atmospheres is pressure 2. Okay, so our value decreased just like we thought it would. Let's look at the next question in your packet. Where is this? A snorkeler takes a syringe filled with 16 milliliters of air from the surface. Okay, I'm going to write. You have 16 milliliters of air, where the pressure is 1.0 atmosphere. The volume in, oh, then it goes down to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure? Okay. Now, people ask a lot, you know, when you're doing the simple gas laws, do I have to always change the volume into liters? Okay, because you're going to see for the ideal gas law, that is a requirement. Liters is a requirement for the ideal gas law. In your simple gas law, it's kind of like when we did the dilution problems and we did M1V1 equals M2V2. Your volume units will cancel out. So as long as your volume units are the same unit, you don't have to put them in terms of liters. But you can if it makes you more comfortable. Okay? So a lot of people do like to do that so that they're constantly like training themselves to put their volume in terms of liters so they don't forget to do it when they're doing the ideal gas law. So you can do that if you would like to as well. So we have P1, V1 equals P2, V2. So we have 1.0 atmospheres times 0.016 liters equals P2 times 0.0075 liters. Okay. Do a little calculation here. 0.016 divided by 0.0075, and we get 2.1. And now in this case, we were taking a pressure of 16 milliliters and decreasing it, or not a pressure, a volume of 16 milliliters, and we were decreasing the volume to 7.5 milliliters. So we decreased the volume. If we're decreasing the volume, we would expect to increase the pressure, and that's exactly what happens here. So again, these are examples of Boyle's law, okay, which is our inverse relationship between pressure and volume. So now we're going to move on. Okay, our next simple gas law that we're looking at is called Charles' law, and that is going to relate volume and temperature to one another as long as pressure and moles of gas are held constant. Okay, and this relationship is a direct relationship, So that means that when one increases, the other must increase as well. When one decreases, the other must decrease as well. Okay, and this will be true when the moles of gas and the pressure are held constant. Okay, so this is our actual formula relationship down here. V1 over T1 equals V2 over T2. I don't know why there's an extra little sign, equal sign there, but that's fine. What you need to keep in mind for this relationship is that this temperature must be in Kelvin, okay? This is because there are no negative Kelvin temperatures. 0 Kelvin is absolute zero, but there are 0 degrees Celsius and there are negative degrees Celsius, and that would mess this relationship up, okay? So we have to use a temperature that is in Kelvin so that we don't kind of destroy the relationship between these two things mathematically by accident. All right, so every temperature value that you get, convert it into Kelvin before you try to use it in one of these formulas. Okay, but let's look what happens here. I mean, this is one of the simple gas laws that people usually are very familiar with, because you see it physically happening all the time. Like if you went to go get like some balloons for a birthday party or something, and you went into Party City and the air conditioning is really nice and it's like middle of July, and then you bring your balloons outside and it's blazing hot out, and all of a sudden you're like, holy crap, why did my balloons all pop? And this is an example of Charles' law. Okay, because if you have the pressure, the atmospheric pressure and the amount of gas, and you hold them constant, and you change the temperature, right? In this case, we're going from ice water to boiling water. Well, in a cold space, doesn't need as much room. Everything's moving real slow. Everything's like chilled out, literally. But as soon as you increase the temperature, well, now you've increased the kinetic energy. Things are going to be starting to move around faster. And if the pressure can't be altered at all, the volume is going to have to increase to accommodate that. Okay. So for our pressure to remain constant, our gas has to occupy a larger space. So it starts to actually expand. So something like a balloon will get much bigger as your temperature increases. And this is so we can actually decrease the number of collisions. That's what holds the pressure constant. If you speed up your particles by increasing the temperature, and naturally they would start to collide more and more with the surface around them. The best way to keep the number of collisions that are happening constant is to increase the volume that the gas occupies, so that you can actually hold the number of collisions to the exact value that you want it. That's what ends up happening there. So let's look at some examples of Charles' law. Let me switch back to the whiteboard so that we can work these out. Okay. A sample of gas has a volume of 2.80 liters. At an unknown temperature, when the sample is submerged in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What is its initial temperature in Kelvin and in Celsius? Okay, so this is our information that's paired up properly. So we have 0.00 degrees Celsius. We're going to turn this into Kelvin. Just did the steps to remind everybody who might have forgotten what our Kelvin calculation looks like. And now we're going to use Charles' law. So that's going to be V1 over T1 equals V2 over T2. And it doesn't matter which pair you call V1 or V2, you just have to make sure that you pair up the temperature and the volume correctly. Okay? So in this case, I'll say that I have 2.80 liters divided by X, because I don't know what the corresponding temperature is. And that will equal 2.57 liters divided by 273.15 Kelvin. Okay, so now I need to cross multiply to solve this. 2.80 liters times 273.15 Kelvin equals 2.75 liters times X. Like to watch the units all cancel out. Makes me happy. So 2.8 times 273.15 divided by 2.75 equals, oops. Let's pretend that I didn't make this mistake. Just go back and fix everything real quick. Okay, wait, put it back in. 2.8 times 273.15 divided by 2.57, and I get 200. Where am I at? My X over here, T1 equals 298 Kelvin. And then if I want to solve this for Celsius, I'm going to take away 273.15. And I get like 24 degrees Celsius. Ooh, sorry for that little number inversion. Okay. So hopefully that all makes sense. I'm going to look at another example. I think we have another example on the packet here. Yeah, we have a gas cylinder with a movable piston, has an initial volume of 8.82 liters. Okay, so volume initial. If we heat the gas from 35 degrees Celsius, so temperature initial is going to be 35 degrees Celsius, and we heat it to 155 degrees Celsius, what is its final volume? Okay, so now we have a slightly different setup here, but we're going to tackle it the same way. First thing we're going to do is we're going to take these temperature values and we are going to put them in terms of Kelvin. So 35 plus 273.15. That's going to be 308 Kelvin. 155 plus 273.15 is 428 Kelvin. Okay, so now we get our V1 over T1 equals V2 over T2. 8.82 liters over 308 Kelvin equals VF over, or V2. Doesn't matter what you call it. You can call it X if you want to. Over 428 Kelvin. Okay. And this will be 8.82 liters times 428 Kelvin equals V2 times 308 Kelvin. Okay, so 8.82 times 428 divided by 308, and that will give us 12.3 liters for our final volume. The next of the simple gas laws is called Gay-Lussac's law, and this one is very closely related to Charles' law. instead of dealing with volume, it deals with pressure and temperature. The relationship is still direct one. So as pressure increases, temperature increases. As pressure decreases, temperature decreases, assuming that the amount of gas and the volume of gas is kept constant. Okay, but you see we end up with the same relationship here. We can use the three gas laws that we just talked about to form what's called the combined gas law. And that relates the pressure, volume, and temperature of one sample to another sample, as long as we're not dealing with the number of moles of gas as something that's changing. Okay, so if we can keep that moles of gas constant, then we can relate the pressure, volume, and temperature of a sample at one set of circumstances to the pressure, volume, and temperature at another set of circumstances. Stupid extra equal sign in here. Just ignore that. I don't have an example of this in this PowerPoint right here, but I feel like there are some in your textbook once you finish the simple gas law questions in the back of your textbook. So look for those. The combined gas law, it's not like a named law, you know, it's not Boyle's law, it's not Charles' law, it's just what happens when you do combine them. So if you're given the pressure, the volume, and the temperature, and then the pressure and the volume, you should be able to find the final temperature, okay? You do this the same way that we just looked at Boyle's law, Charles' law, Gay-Lussac's law, okay? The last of the simple gas laws that we're going to talk about is called Avogadro's law, and that's the law of combining volumes, or it's not the law, it's paired up with the law of combining volumes. Avogadro's law talks about a direct relationship between the moles of gas that are present and the volume of gas, assuming that the pressure and the temperature are constant. So you can imagine that if there are more moles of gas present, if there's a greater number of moles, the volume would need to increase to accommodate that number. That's basically Avogadro's law in a nutshell. So as one of them increases, the other one will increase. As one decreases, the other decreases. It's another direct relationship. And this is the mathematical relationship between them. Again, ignore that. So volume 1 over sample 1 in moles equals volume 2 over sample 2 in moles. And again, like all the other simple gas laws, this is going to be true if we hold the other two factors constant. So we have a constant pressure and a constant temperature here. The equal volume of gases contain an equal number of moles, regardless of the type of gas that's present. Okay, this is true for a lot of different gases. The type of gas doesn't matter in a lot of these calculations, and this is definitely true for Avogadro's law. Between Gay-Lussac and Avogadro, that's when we come up with what's called the law of combining volumes. And we can start relating balanced chemical equations that have gases as their states in them. We could start relating them to volumes of gases, okay? And what I mean by this is that when we see a balanced equation, so this is a pretty standard balanced equation, 2 H2 gas plus 1 O2 gas is 2 H2O gas. We've been reading this all semester as 2 moles of H2 plus 1 mole of O2 equals 2 moles of H2O. But it turns out that when we're dealing with gases, we can also read this as 2 liters of hydrogen plus 1 liter of oxygen will give me 2 liters of H2O gas. Or 2 molecules of hydrogen plus 1 molecule of oxygen will give me 2 molecules of H2O. Okay, but this relationship, this relationship that allows us to express mole relationships as volume relationships can be very helpful when we're trying to find information out about gases in a chemical reaction. Okay, so highlight that and put that aside for later. That's your law of combining volumes. Let's do an Avogadro's law calculation now. I'll go back to my whiteboard for this. Okay. So we have an athlete in a kinesiology research study, has a lung volume of 6.15 liters. During a deep inhalation. At this volume, his lung contains 0.254 moles of air. During his exhalation, his lung volume decreases to 2.55 liters. How many moles of gas did the athlete exhale, assuming constant temperature and pressure? Okay. So we have volume and we have moles of gas here. This means that we're going to be setting up Avogadro's law. So that's V1 over N1 equals V2 over N2. So V1 will be our 6.15 liters over 0.254 moles of gas, and that will equal 2.55 liters over X. This is how many moles of gas are left. Okay, so now we solve this out. 6.15 liters times X equals 2.55 liters times 0.254 moles divided by 6.15 liters divided by 6.15 liters. Okay. 2. Times 0.254 divided by 6.15. 105 moles of gas are left over. Now, read your question, okay? Because this asks you how many moles of gas were exhaled. This is the moles that you started with. This is the moles that are left. So the amount that's exhaled is the difference between these two things. Okay, so our moles that are exhaled is our 0.254 moles minus the moles that are left over. Okay. 0.254. So that's 0.149 moles that are actually exhaled, the difference between those values. Okay, hopefully that makes sense. So now we're going to look at next example. A chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of gaseous product if the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters. What was its volume after the reaction? Assume constant pressure and temperature and that the initial amount of gas completely reacts. Okay. So this one's a little more straightforward. We have V1 over N1 equals V2 over N2. Okay, so we started with a cylinder that contained 0.120 moles of gas at 2.18 liters. So let's make that V1 and N1. Okay, and then our second scenario, we produced 0.621 moles of gaseous product. And the part of the sentence, the last part of that sentence, that the initial amount of gas reacts completely, that's their way of telling us that this mole value is not going to be added on to this value, that this has been consumed, and now we have 0.621 moles of product, and that's the entire amount of gas moles that are going to be present in our piston. Okay, so that becomes our mole value. And then we want to know what this volume is. Okay, so we have 0.120 moles times V2 equals 2.18 liters times 0.621 moles and let's see what we get. 2.18 times 0.621 divided by 0.120. We have volume 2 equals 11.3 liters. Sorry, guys. Just looked back at my screen and saw that you couldn't see any of that. Okay. So now you got enough time to look at that. Hopefully that makes sense. That's the last of our simple gas laws. And now we're going to look at combining them into the ideal gas law. So we're going to take a much closer look at the ideal gas law now. Okay, so now we are going to look at the ideal gas law. This is a summary of all of our simple gas laws. All right, in the ideal gas law, it's called the ideal gas law, first of all, because it talks about this relationship in terms of ideal gases. Okay, and ideal gases are gases that are at, they have specific properties to them. Okay, don't worry too much about that now. We're going to discuss that later on in the chapter, the difference between an ideal gas versus what we'll call a real gas. But for now, we'll assume that all of the gases that we're looking at are ideal gases. So the ideal gas law says that the pressure times the volume of a gas equals the moles of gas times R, which is our gas constant, times the temperature. Okay, that's how the gases relate to one another. In the ideal gas law, the R is our gas constant, and the value of R, the numerical value of R, depends on the units that are used to calculate it. Okay, so the R gas constant that we are using is 0.08206 liters times atmosphere divided by moles times Kelvin. So the units that are attached to this gas constant, they are going to determine the units that we are allowed to use to calculate our ideal gas law. All right, we have to only use units in the rest of our ideal gas law that we find in our gas constant. Okay, so I thought I might have had one more slide where I had this laid out a little more clearly. So for pressure, we are going to have all of our units converted into atmospheres. For volume, we're going to convert all of our volumes into liters. For the amount of gas that we have, we'll convert those values into moles. And every temperature value will be in Kelvin. Okay, those are our only possibilities. And as long as we know, as long as we know a few of these, we can find our missing variables. Okay, and we're going to practice some of that now. So I think there's a few of these ideal gas law questions, and we're going to just run through them on the whiteboard. Okay, we'll get real good at this. Okay, let me bring that question back up so I can see the numbers. All right, so the first question is calculate the volume occupied by 0.845 moles of gas, of nitrogen gas, at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. Now, this is the nicest kind of ideal gas law question because all of our variables are given to us in the units that we need in order to solve the ideal gas law. In reality, that almost never happens, but it's a good starting point, right? So we're going to start off by writing out PV equals nRT. Okay, and we'll substitute in the things that we have. So we have our pressure. That's 1.37 atmospheres. We are looking for the volume, so we know that we don't have that. Our moles of gas is 0.845. Our R value is 0.08206. I think that mastering chemistry shortens that down to 0.0821, and that's fine. And then our units, liters, atmosphere, over moles times Kelvin. And then our temperature, 315 Kelvin. And now look what happens in terms of units as, as we're multiplying these things. So our moles goes away right there. Our Kelvin goes away over here. Okay, so now we are going to divide both sides by 1.37 atmospheres. Okay, and what happens here? That unit goes away. So we already see that we're going to be left with a unit of liters when we're done with this calculation. And so now let's break out the calculator. 0.845 times 0.08206 times 315 divided by 1.37. Okay, we get a volume value of 15.9 liters. Okay, example 1 for our ideal gas law. Let's look at the next example, number 2 on your slides. An 8.50 liter tire, write this down, 8.50 liter tire contains 0.552 moles of gas. At a temperature of 305 Kelvin. What is the pressure in atmospheres and in PSI of the gas in the tire? All right, so we'll start off the same way. PV equals nRT. Pressure times volume equals 0.52 moles times 0.08206 times 305 Kelvin. Okay, and then we'll divide this. Okay, and we'll watch all of our units cancel out. Okay, so in this case, we're left with the unit of atmospheres. 0.552 times 0.08206 times 305 divided by 8.5. So my pressure is going to be 1.63 atmospheres. And then to figure out how many PSI that is, we're going to go back to our chart with all of our different pressure units in it. And we'll see that 1 atmosphere is 14.7 PSI. And that will give us a pressure of 23.9 PSI. Okay. Let's look at the next example. Calculate the number of moles of gas in a 3.24 liter basketball inflated to a total pressure of 24.3 PSI at 25 degrees Celsius. Okay, this is getting a little more real now because we're starting to see values that are not in our perfect pre-ready to plug in ideal gas law values. So we have a volume of 3.42 liters. We have a pressure of 24.3 PSI. And we have a temperature of 25 degrees Celsius. Okay, so now the first thing we want to do is turn these values into ideal gas law values. So my PSI, 14.7 PSI in 1 atmosphere. (24.3) divided by 14.7 is 1.65 atm. 25 degrees Celsius plus 273.15 equals 298 Kelvin. Now we're ready for the ideal gas law. Okay, but we can't do the ideal gas law without doing those 2 steps first. So now we have PV equals nRT. So our pressure is going to be 1.65 atm times 3.24 liters equals this moles of gas value that we don't know yet times 0.08206 liters times atmospheres over moles times Kelvin times 298 Kelvin. Okay. Now we want to isolate our mole value in this case. So we'll divide this side by 0.08206 divided by 298 Kelvin, and we'll do the same thing over here. I got a little sloppy, sorry. Okay, so these cancel out here. Over here, just that cancels out, liters cancels out, atmospheres cancels out, and now moles will be our unit that's left. Okay, so we have 1.65 times 3.24 divided by 0.08206 divided by 298. Okay, and we get a mole value of 0.219 moles. That's our missing mole value. Okay, let's look at this next question. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters mercury and a temperature of 58 degrees Celsius. Okay, so step one, right? First, we are going to put all of our units in terms of ideal gas law units. So we have this 750 millimeters of mercury. No, thank you. So 760 millimeters of mercury are in 1 atmosphere. 715 divided by 760 is 0.941 atmosphere. Okay, 58 degrees Celsius plus 273.15 is going to be 331 Kelvin. Now we are ready to go. So PV equals nRT. So 0.941 atmosphere times our unknown volume is 0.556 moles times R times T. Okay, and I'll divide this both sides by our pressure. We will cancel out our units. Okay, so do some math. 0.556 times 0.08206 times 331 divided by 0.941. That gives us 16.0 liters, and that is our volume. See, these aren't that bad. Ideal gas law is pretty okay. It can get a little bit more complicated. And when I say complicated, I don't mean difficult. I mean more steps, like more kind of annoying math that we have to do. And this is exemplified in the next problem. This will be our last example before we kind of move on to a little more discussion. Okay, so if we look at the next problem now, it's kind of everything's all messed up in this problem. So we want to know what the pressure in millimeters of mercury is of a 0.133 gram sample of helium gas in 648 milliliter container at a temperature of 32 degrees Celsius. All right, so everything about this problem is just a little bit annoying. Not hard, just annoying. So we have to fix everything. Okay, so first of all, this gram value, we can't have an amount of gas that's in grams. We have to have mole amounts to put into the ideal gas law. So we're gonna have to take this gram amount and we're gonna have to convert it into moles. So we're gonna look at our periodic table, look up helium. All right, we got 4 grams of helium. For every 1 mole of helium, so 0.133 grams is going to be 0.03325 moles of helium. Great. Our volume value here is in milliliters. No good. We have to convert it into liters. There's 1,000 milliliters in every liter. So 0.648 liters. Our temperature, we have to put into Kelvin. So that's going to be 305 Kelvin. Now that we have everything in terms of our ideal gas law variables, now we can use the ideal gas law. Okay, so PV equals nRT. We don't know what the pressure is. We want to solve for that. Our volume is 0.648 liters. Our mole value is 0.03325 times our constant, 0.08206, liters times atmospheres over moles times Kelvin, times 305 Kelvin. Okay, now we'll divide both sides by 0.648 liters. Watch our units cancel out. Okay, so our pressure is going to be 0.03325 times 0.08206 times 305 divided by 0.648, and that gives us 1.28 atmospheres. But we wanted a final pressure in terms of millimeters of mercury. So every 1 atmosphere is 760 millimeters of mercury exactly. So that is 976 millimeters of mercury. And that is our final answer. See, so it's still not hard. It got a little bit more annoying, but it wasn't hard. All right, let's go back to our PowerPoint. Okay, so when we are talking about sets of gases, it's sometimes helpful for us to have a standard set of conditions that we can compare gases at, right? Because if we have a standard set of conditions, then we're looking at differences in them that are not related to things like temperature variations or pressure variations, right? That set of conditions for us is called STP, or standard temperature and pressure, all right? So if you hear the term STP in terms of gases, you should automatically assume that it is 1 atmosphere and the standard temperature is 273 Kelvin or 0 degrees Celsius. The unit does not matter, the value matters. So any pressure value that equates to 1 atmosphere is standard pressure. Any temperature that equates to 273 Kelvin is a standard temperature. Okay, if we make certain comparisons at standard temperature and pressure, we're able to find out some other useful information about the different gases. One of these pieces of information that we can find out is what's called the molar volume of a gas. The definition of molar volume is literally the volume that 1 mole of any gas occupies when it's at standard temperature and pressure. So what volume a 1 mole of gas occupies when the temperature is 273 Kelvin and the pressure is 1 atmosphere. And if we look at the ideal gas law, we can calculate the molar volume, and it is the same for every single gas. It does not matter what the gas is, right? If we solve the ideal gas law for volume, so volume equals moles of gas times R times T divided by P. If we're using 1 mole of gas at standard temperature and standard pressure, every single type of gas, doesn't matter what it is, any gas will occupy 22.4 liters at this set of conditions. So 1 mole of any gas at standard temperature and pressure is going to occupy 22.4 liters of space. okay? That means that 6.022 times 10 to the 23, Avogadro's number of molecules of gas, will always occupy 22.4 liters of space when we're at 1 atmosphere and 273 Kelvin, STP. The type of gas does not matter, okay? So this particular volume is called the molar volume. I know I'm being repetitive, but I really want this to sink in for you. So that is the molar volume. The volume of 1 mole of gas at standard temperature and pressure is the molar volume. The molar volume is 22.4 liters. We can use the molar volume of a gas at standard temperature and pressure to figure out what the density of a gas at standard temperature and pressure would be as well. The density of gases is going to be given in units of grams per liter, okay? Density is mass over volume. In the case of gases, the mass is grams, the volume is liters. So density is going to be grams per liter. The mass of a mole of gas is going to be its molar mass, because molar mass is grams per 1 mole. Okay. The volume of 1 mole of gas at STP is 22.4 liters per 1 mole. So if we want to know what the density of gas is at standard temperature and pressure, we can take the molar mass, which is grams per mole, and divide it by the molar volume, which is liters per mole. And we'll end up with the density of gas in grams per liter. So 2 examples of that. The density of helium at STP is 4 grams per mole over 22.4 liters per mole. And that's the density of helium, 0.179 grams per liter. A larger or a more massive gas, which is nitrogen gas, is 28.02 grams per mole divided by 22.4 liters per mole. So the density of nitrogen gas would be 1.25 grams per liter. See how our little moles, they cancel out there. But we don't always have the standard temperature and pressure conditions available to us. So we need to figure out a way to find the density of gas when we are not at standard temperature and pressure. Okay, I know there's a lot going on in this slide, so just try to listen as I talk through it. Don't worry about interpreting it on your own. We know that density is mass over volume. So what we're basically looking for is a way to figure out how to make a similar relationship using the ideal gas law. Okay, and that's what's going on in this whole situation here. So we've already defined the density. I'm going to go back a slide here, 2 slides. We've already defined the density of a gas as the molar mass divided by the molar volume, right? But the molar volume's STP dependent, so we have to find a way to get around this molar volume. That's what we're doing here. So if the density of the gas is the molar mass divided by the molar volume, well, how can we kind of fix this molar volume relationship here? Well, density is mass over liters, so we could say that the volume is mass over density. Okay, and this is not at STP. Now, if we take our ideal gas law and we pull out parts of it that are related to our molar mass and our volume, we can like substitute these variables for variables that we could use to find the density of a gas. Okay, so we know that if we want to find the moles of a gas, we can use the mass of the gas and we can use the molar mass. Okay, that we can substitute in to the mole variable part of our ideal gas law. To find the volume of the gas, we can use the mass of a gas and its density, right? We get that relationship down here from the definition of density. Now, if we take that relationship and we substitute it into the volume portion of the ideal gas law, now we have a way to incorporate density into our ideal gas law. What we end up with if we do that is this compound fraction, okay? Which again, looks more complicated than it is. But that N over V, if we put our substitutions in, it's moles is grams divided by molar mass, volume is grams divided by density. Our gram values cancel out of this calculation. And what we end up with is just density and molar mass as part of this equation here. Okay. I'm going to finish solving this out on the whiteboard because I skipped a step before I got to density, and I don't know if I know that like some people enjoy watching the derivation like for understanding purposes. I know some of you guys have like checked out of the derivation right now and you're like, just tell me the final results. But give me a second I want to just finish solving this on the whiteboard. Okay, so this compound fraction here, if we want to solve that, you do your keep, change, flip situation. So we have grams over molar mass times density over grams. And that's how we end up solving. So our grams cancel out, and this is equivalent to density over molar mass. And that's going to be equal to the rest of our ideal gas law, which is P over RT. Now, if we want to solve this equation for density, which we do because we want to weigh, make that look more like a P. We want a way to solve for the density of a gas when we're not at standard temperature and pressure. So now we're going to multiply both sides by molar mass. And our density equation comes out of that. So density of a gas equals pressure times molar mass divided by RT. Okay. Now the derivation is not something that you need to be able to replicate or anything like that. You do need to know this. Okay. You have to be able to find the density of a gas if you are not at standard temperature and pressure. So actually, that being said, let's just solve some of these examples that are in your packet. Okay. Calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeters of mercury. Okay, so here's the thing too in this chapter. You see this question, it says calculate the density of nitrogen gas. Nitrogen gas, and you have to know this. Remember in chapter 2 maybe? It was either chapter 2 or chapter 3 where we had the diatomic elements outlined. You have to know those still. Okay, so when they tell you nitrogen gas, you have to know that nitrogen gas is N2. It is not N. N doesn't exist. And you have to be very clear about that in your own mind, right? There are diatomic gases that exist, and they only exist in this paired form. You have to know what gases those are. So to answer this question, we have to know that nitrogen gas is N2 because our density equation is pressure times molar mass divided by R times T. So if we're using the molar mass of nitrogen, but we only have one nitrogen in our formula, that's going to be a different calculation, right? We don't want to do that. So we're going to look for these variables so we can plug it into our density equation right now. So we have nitrogen gas. The molar mass of nitrogen gas is 14.01 times 2. That's 28.02 grams per mole. We have a temperature of 125 degrees Celsius. So we're going to add Our 273.15 to that. That's 398 Kelvin. And what else do we have? A pressure of 755 millimeters of mercury, which we'll immediately put into atmospheres. And that's 0.993 atmospheres. Okay. Yeah, now it looks like we have enough to solve. So, down here. So density will be pressure, which is 0.993 atm, times molar mass, which is 28.02 grams per mole, divided by R, 0.08206 liters times atmospheres over moles times Kelvin, times temperature, which is 398 Kelvin. Okay, now before we do a calculation, let's look at how our units cancel out here. We have atmosphere taking care of atmosphere there. We have moles taking care of moles, Kelvin, Kelvin. And what are we left with? We're left with grams and we're left with liters, which we already said were the units of density for gases. So we're on the right track there. So now let's do some calculator work. 0.993 times 28.02 divided by 0.08206 divided by 398. And we get a density of 0.852 grams per liter. Okay, so pretty straightforward. Once we have our density equation, getting the density equation was maybe a little bit convoluted, but using the density equation is very straightforward. Let's look at another example. A gas has a density of 1.43 grams per liter at a temperature of 23 degrees Celsius and a pressure of 0.789 atmospheres. Calculate the molar mass, okay? So first thing we'll do is take that Celsius and we'll add 273.15 to it. Okay, so that's 296 Kelvin. And now let's write out our density equation. Pressure times molar mass over R times T. Okay, so in this case, we have a little bit of a different setup because we have a different unknown. In this case, our molar masses are unknown. So we have 1.43 grams per liter equals 0.789 atmospheres times molar mass divided by 0.08206 liters times atmospheres over moles times Kelvin times 296 Kelvin. Okay, now we want to isolate the molar mass here. Okay, so we're going to have to take our 1.43 grams, yeah, like that, grams per liter. Okay, we're going to divide this side by 0.789 atmospheres. All right. Hopefully that makes sense. So we're going to divide this side by 0.789 atmospheres. We're going to multiply both sides by this denominator. So I'll have 0.08206. And then what we're left with will be the molar mass. Okay, so we've isolated this variable. So cancel out some units. Notice the units that we're left with here are grams and moles, which is the units of molar mass. Okay, so 1.43 times 0.08206 times 296 divided by 0.789, we get, move that up a little bit, 44.0 grams per mole is the molar mass of this gas that we're looking at. Okay. And let's look at one more example. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury. And a temperature of 45 degrees Celsius. To do this question, you know, that's going to require you to actually look at your periodic table, okay? Because they're telling you the identity of the gas, but they're not telling you what the numerical value of the molar mass is. So you know that it's xenon. So if you look on your periodic table, you see that, I have to look it up here, hold on. Okay. It's like 131.29, I think. I'm trying to read this periodic table, but it's a little bit too small for my eyes. But I think that it's that. So we have to find that molar mass before we can proceed. Okay. Once you have it though, density is going to be pressure temperature and then we have our molar mass. So pressure times molar mass over R and T. .976 times 131.29 divided by 0.08206 divided by 318. That's 4.91 grams per liter. Okay. Okay, so now let's look at how we can calculate the molar mass of a gas in some other ways. Okay. To do this, we have to focus on what the definition of the molar mass of a gas is, and that's just that it is the mass of the gas, or the gram value, divided by the mole value. So anytime that we know the mass of a gas, and we can calculate its mole value, the number of moles that are present, we can find the molar mass of a gas by dividing those two values, okay? Because molar mass is just grams of gas divided by the moles of a gas. So for example here, a sample of gas has a mass of 0.311 grams, its volume is 0.225 liters at a temperature of 55 degrees Celsius and a pressure of 886 millimeters mercury. Find its molar mass. Okay, if we want to know the molar mass, then we need the grams of the gas and the moles of the gas. We're given the grams of the gas here. Okay, we can use the ideal gas law to find its mole value because we have a volume, we have a temperature, and we have a pressure. So the first step, we are going to use PV equals nRT, and we are going to solve this for the moles of a gas. We need to convert the pressure into atmosphere, and we need to convert the temperature into Kelvin. Once both of those things are done, then we can solve for moles of a gas using the ideal gas law. Okay, so we get 9.7454 times 10 to the negative 3 moles of the gas. Now we can use the definition of molar mass, which is grams divided by moles, and we can divide those two values, and now we know the molar mass of a gas is 31.9 grams per mole. Okay, let's look at this second example. Okay, a gas has a mass of 827 milligrams. 827 milligrams is 0.827 grams. Remember, molar mass is grams divided by moles, so we want to have everything in the right units. Our temperature is 88 degrees Celsius. We want to turn that into Kelvin. So 88 plus 273.15 will be 361 Kelvin. We have a pressure of 975 millimeters of mercury. We want to divide that by 760 to figure out the atmospheres. So we have 975 millimeters of mercury, and that is equivalent to 1.28 atmospheres. With that information, we can solve our ideal gas law for moles. So it's going to be pressure times volume, 1.28 atmospheres times 0.270 liters over RT, 0.08206. (361 Kelvin). Do some calculator work. Okay, and we get a mole value of 0.0117. So now our molar mass is going to be our gram amount divided by our mole amount. So our gram amount is 0.827 grams divided by 0.0117 moles. And that is 70.7 grams per mole. Okay. Okay, our next topic is going to be mixtures of gases. But I'm actually going to stop this recording here because it's gone on a little longer than I thought it would. I'm going to come back with a pretty short follow-up to this to finish up mixtures of gases and collecting gases over water. But I just, yeah, I want to stop this here to break it up into pieces. Okay, so I'll record that one in a few minutes.